let's talk about where we're at today. Actually, before we talk about where we're at today, as a reminder, folks, if there's anybody in here who has one of the two evals that we've already done, has done that but has not got it back, then I will have those here with me, and you're absolutely welcome and encouraged to swing by on the way out and just pick it up from me so I don't keep carrying them around forever. Hope you all had a good weekend. We are starting chapter 4 today. One of the things I really love about chapter 4, and I hope you'll find the same, is that here we're finally putting all the pieces together. All the things we saw back on day 1 and the utilization of free body diagrams and equations of equilibrium to help us evaluate, analyze forces within a system. The details that we've learned since then, things like, for example, what's a moment, Brignon theorem, stuff like that, much, much more. All these things now come together in chapter 4 and lead us to the culmination of when we're done with chapter 4, we are able to analyze more complex mechanical systems. In fact, chapter 4 is going to be broken into 2 sections. One is a section in which we're going to take a look at trusses. Today we're going to focus on trusses. And we'll talk about trusses for a couple of days, probably at least through Thursday, possibly just a little bit longer. But then we move into the frames and machines portion of chapter 4, which the can crusher that we saw on day 1, that was an example of a machine. That's a machine type problem. So that gets us kind of where we said we were going to get to. We'll be into that by next week for sure. But for today, we're going to talk about trusses. Now, to also punctuate one last thing about that, when I say as we get through chapter 4, we will have the ability to analyze these things, the question then naturally becomes, okay, so what's coming after chapter 4? Answer. After chapter 4, we're going to stop ignoring some of the things that we've had to ignore so far. For example, once we get in chapter 5, we're going to be interested in things like, well, how do we handle distributed loads? Because we talked about that from day 1. Forces really aren't just little point things. They're usually distributed over some sort of a finite area. How do we handle that? We're going to see about that in chapter 5. We're going to stop neglecting weights in chapter 5. We're going to be more interested in what the weight of certain mechanical elements will be. That too, coming again in chapter 5. In chapter 6, we look at friction. We've just ignored friction throughout the entire course, but we're going to stop ignoring friction. But guarantee you this, by the time we get there in chapter 6, I guarantee that if you've done what you needed to do up until that point in time where you've really learned the fundamentals, especially the stuff we're covering today here in chapter 4 and what we'll be covering the next couple of weeks here in chapter 4, if you've done that, then I promise you, you're going to shrug your shoulders when it comes to friction. You're going to say, is that all? Because there really isn't that much more to it. And then we'll end the whole thing, as we talked about at the very beginning, by taking just a couple of days to take a look at 3D stacks to make sure we check that box off. But today's business is trusses. Trusses. There's a definition that I put up on the board here, folks, and I want you to know I just spontaneously wrote this. This doesn't come out of any book or anything like that, but if I had to say to you, hey, what exactly, or how would I describe a truss in one sentence, that one there does it. It's any collection of connected two-force members such that each member forms a leg of a triangle. So, for example, if I had a two-force member that looked like this. Now, let's remember, what exactly is a two-force member, or what constitutes a two-force member? Criteria. Number 1, two-force members can have a grand total of 2 pinholes, no more, no less, and no other supports. No other supports other than 2 pinholes. They can be any shape. We couldn't care less what the shape of this is. All that matters is there's 2 pinholes. Number 3, there can be no weight. A two-force member is ultimately, by its nature, utter nonsense because everything has weight, but they don't. But that's okay. We will treat everything as weightless for now because when it comes to trusses, these things actually make analyzing a truss real real doable, let's put it that way. And then lastly, a two-force member can't have any forces applied to it. Now this is interesting because in trusses we talk about connecting these things all up. And of course a truss by its nature is designed to manage loads. So for example, where have we all seen trusses before? Look at any house being built that's got a triangular shaped roof and the structures underneath that are trusses. Look at old style bridges crossing rivers, gorges, what have you. All those triangular shaped elements on the bridges, trusses. We've seen trusses. Trusses are very, very common. They're common in equipment that's used to, like for example, go to a concert and look at the lighting that's hung up over the stage, usually going to be hanging from some sort of a truss fixture. So we see these things all the time. They are by their nature designed to handle loads. The roofs of our houses naturally are designed to handle the roof itself, the outer boards, the shingles, all that kind of stuff. But hey, I don't know about you, but I'm guessing if I'm going to live in Michigan or any part of the northern part of our country or any place where we get a lot of snow, I'm going to be a whole lot happier if I know that the truss that's holding up my roof is designed to handle those occasional heavy snows that could be hanging up there for a couple of days in the wintertime. Yet, we're talking about a two-force member that, wait a minute, it can't have any load, right? How do we get around that? Simple. In a truss with a two-force member, if there's a load applied, we don't apply it on the two-force member. We apply it on the pin. All right, so we're going to see that as we go along. But back to the definition. Any collection, connected by pins, of course. Two force members such that each member forms a leg of a triangle. So if I have a two-force member that looks like this, and let's say I have another two-force member that behind it that comes out and looks like this, let's say, and there's another pin here, so now I got a second two-force member. Let's say I got yet another two-force member here that's coming down and looking like this. All right, now, I have three two-force members there. Does that make a truss? No, because they're not connected. So remember, collection of connected two-force members such that each leg forms a leg of a triangle. So what I'm saying there is if I added now a fourth two-force member, like right here, and I connect that up, now they're all connected, yeah, but they don't form triangles. So is that a truss? No. And think about this, folks. If I really did have four two-force members like Z right here, and I've got these things all connected up by merely pins, is there any way that I could actually hold that connected square, in this case, of two force members and just kind of toss it out to you and assume that it's going to have the same shape when it lands on you? Nope, not at all. So what would make this a truss? Add one more two force member. It can go diagonally here, it can go diagonally here. It doesn't make a bit of difference. But if I have now another two force member, goes around like so, now I've got a collection of two force members, all interconnected, such that each member forms a leg of a triangle. That right there, folks, is a truss. That right there, too, if I did connect this all up and flip it out at you, we play a little truss frisbee here. When you catch that frisbee, it's going to look just like that. And it would look the same, of course, if we had this diagonal leg going over like so. Now, when it comes to analyzing these things, we don't just have them floating in midair like that. We usually are going to have them supported by something. So think about, for example, a truss that might be designed to go over, like, let's say, some sort of a cutout in the ground, like a riverbed or a gorge or something like that. In this case, what we're going to see, and I'll let you do it over here. Let me extend this truss just a little bit here, folks. Just want to make this look a little bit different so that we got a little bit more context here. So I'm going to add in another collection of two force members here, and let's say that I got this one coming up like so, this one coming down here like so. And by the way, so now I just added in a grand total here of two more two force members. Do I still have a truss in what you see right there? The answer is, once again, yup, because all these two force members are connected together, and each one forms a leg of a triangle, or in some cases, legs of multiple triangles. Take this one here, for example. This truss is a leg of that triangle as well as a leg of that triangle right there. You can certainly do that. But we were talking about how we would support these things. So let's say that this is a truss that's designed just to hang something. I want to hang some kind of a load from over here and support that load. We're going to see throughout our analysis of trusses that we have a common way of showing these things supported. The common way involves, let me draw it first, then we'll talk about it, folks. I want to draw this first, then we'll talk about it. Now, what you see right there, folks, is an example of the common way that we're going to show trusses being supported. Note that the common way always involves one pin connection and one roller connection. Now, do we see that in real life? No. Actually, do we make trusses out of two force members in real life? No, we don't do that either, right? So if we think about the trusses that are holding up the roof of our house, they're not a bunch of 2x4s that are all pinned together. They're a bunch of 2x4s that are either nailed together, bolted together. There can be all connected plates that go over them, all kinds of ways of doing that. If you look at a truss in an industrial application or like going over a bridge or something like that, you might see that those trusses are bolted together, maybe welded together. So doing it with two force members is kind of a bit, again, it's a little bit of nonsense. We don't do that in the real world, but we do that for the purposes of analysis. Again, all that stuff's going to come together here in just a second, but back over to this then. So every time we show trusses supported, it's going to look, I shouldn't say every time, usually it's going to look like this. There's going to be a pin, there's going to be a roller. Now, there can be variants of this. Like, for example, we might have a pin and maybe some tension member, like a cable, holding up the truss. That's perfectly fine too. But there's a reason behind showing this kind of a support system, even though it isn't exactly what we would expect a real life support system to look like, and it is this. I want you all to think about this. Just lean into this diagram you see right here and think about this. Think about what you already know, your knowledge base, what you already know in terms of if you did a free body diagram of this entire truss, you kept everything together, but you took away the support here. That's a pin, right? Folks, everybody should answer this question right here. How many forces do we show for a standard pin connection? What's the grand total number of forces for a standard pin connection? I got a few of you saying 2. Every one of you should be saying 2. X, Y, this is always going to be that way, right? So if I did a free body diagram of this truss right here and I popped out this connection, I'm going to have 2 unknown forces there. Now, on the wheel, assume that thing is frictionless, where that wheel makes contact with the ground there or whatever that is below that. Same question. How many unknown forces do we have in a wheel connection in a free body diagram? And everybody held up a grand total of 1 finger. It should be an index finger, by the way. Wheels, we simply show as a single normal force, right? So if you think about that free body diagram, if I did a free body diagram of just this truss right here, kept the whole thing together, and I only was interested in these connection forces, these support forces down here, I would have 2 support forces here, 1 support force here, grand total of 3 unknown forces, and what's my budget? Now everybody's going to hold up the number of fingers on this one. What's my budget for equations with 1 free body diagram? 3 equations, 3 unknowns I get to solve. Before I even start asking myself what the heck is going on in this truss, I'm already going to know the forces down here on these supports because we forced the supports into a configuration so that we could solve it. You see, folks, in that we see what analyzing trusses is all about, at least at this level. It's not about really reflecting reality. It's about creating a model that we've got the tools right now to be able to analyze. Think about it. If I had a pin connection here and a pin connection here, 2 pins, I would have a grand total of 4 unknown forces. I don't have enough equations to solve that. Does it mean it can't be done? No, it means we got to get pretty creative in how we do it. There are ways to do it, but why bother? We don't need to do that. Let's just make these nice, simple connections like that, and then we can analyze it and move on from there. So now we know what a truss is. It's always 2 force members, at least for our intents and purposes. and it's always going to have this same kind of support system. So, now what? Well, let's go back to the motivation for why we would analyze anything in terms of a mechanical system. Let's say that I've designed a truss like this, and I'm using these two force members right here. I've got this, and let's say that I'm going to hang from this over here. I'm going to hang a Mack truck. All right, folks, I am going to be dangling a Mack truck from my truss. How many of you believe right now that we could take a bunch of I don't know, meter sticks, let's say. Let's say we get some meter sticks and just poke a couple of holes in the end and hook those together. So I got a meter stick here, so on and so forth like that. How many of you are real confident that you want to stand underneath that Mack truck being held by the meter stick truss? Not seeing any hands go up here. Of course, that's not a surprise, but I know I certainly wouldn't. But on the other hand, let's say your job was to design the truss that could support that. The question becomes, what are you going to make it out of? How are you going to connect it? How are you going to assure that that truss is not going to fail and you got some catastrophic drop of the Mack truck or whatever it is you have hanging up there? Who cares? It could be a bucket of grapes for all we care about. But, right, how are you going to do that? Well, there's a couple of answers. One is, well, gee, Professor, one way I know I could do it is I could use steel for these things, and I'll just make the steel, I don't know, about this big around, and it's only going to cost about $98 million to make it, but that'll hold up the truck. Sure, it's going to hold up the truck. You're not going to be employed next week, but it's going to hold up the truck. The right answer is I can design these truss elements if I know what the forces are in those truss elements. If I know that whatever I've got hanging here, again, could be anything, who cares? Let's say that whatever it is, let's say it's 1,000 pounds. I have something hanging from this truss that's 1,000 pounds right here. How much of that 1,000 pounds of force is going to be manifested in that truss member right there? How much is going to be manifested there, and by extension here, and here, and here, and all those different places? We already know from what we talked about from the beginning of this course that if we can figure out the forces in mechanical elements, then things we're going to learn next semester in solids will teach us how to design those elements with knowledge that they will not fail. And those steps of designing those elements are not a whole lot, it's not overly busy. It's kind of easy as long as you know how to get the forces. So our job here in chapter 4 is to analyze these things, figure out what are the forces in these members. And before we even go there, we already know the answer. We know it's going to be a matter of creating free body diagrams and applying equations of equilibrium. I mean, we can literally stop right now. If we've learned what we intended to learn at the beginning of this class up to today, we could stop right now, and I believe that there's a lot of you in this room that already has the confidence, and by the way, when I say a lot of you in the room, could be all of you, could be 2 of you, I have no idea, but I know this much, by the time we're done, all of you should have the confidence to say, you know what, I can draw a free body diagram of anything I want to, and I can apply equations of equilibrium, and I can solve stuff. If you've already got that confidence, boy, do I like that. I hope that that's where you're at. But if not, let's remind ourselves of something. Look at that truss right now. Is there anything on that truss that we can't draw a free body diagram of? No. What if I want to just bust the truss into a couple of pieces? Could I bust it into a couple of pieces and draw a free body diagram of that? Sure. Could I pop one of those pins out and draw a free body diagram of that? Yep. And is there a free body diagram that you can draw that you can't apply equations of equilibrium to? No. So I'm betting we already know how to do this. The only thing we need to do is actually see a couple of standard ways of going about it that make this pretty doable. So let's go there. Questions on anything I'm talking about here, folks? If you have them, fire away. Don't wait for me. Y'all good so far? All right. Let's take a look at. We're going to take take a look at two different solution techniques for trusses. Each one is a perfectly valid way of solving a truss. The first one we're going to look at, by the way, is called the method of joints. After we see a few examples of the method of joints, we're going to look at a thing called the method of sections. And folks, before you even see either one of these, you need to know they're exactly the same thing. They just look different, but they're exactly the same thing. There's no difference here in how we do it. It's just that the way we can sometimes represent things in a free body diagram can make our analysis a little, not so much easier, but a little bit more direct to what it is we want versus maybe we'll get there, we've got a few extra steps. And I'm cloaking it a little bit, folks, when I say that. Bottom line is this: the method of sections, no, I'm sorry, the method of joints, thing I'm about to show you right now, there's not a truss out there you can't solve with the method of sections. However, sometimes it might take a bunch of steps to get to the point you want to solve using the method of joints. The method of sections sometimes can create a shortcut that can get us there more directly. You'll see that as we go there in just a few minutes. We're going to start things off with the method of sections. And folks, I keep saying method of sections, I mean the method of joints. We're doing the method of joints today. Folks, let me start things off by showing you a sample problem here. And when we get, by the way, as we get to this stage of the game right now, pretty much everything is just, well, let's just work problems. There's not a whole lot to talk about. It's just, let's just demonstrate. So let me draw a truss up here. This is actually out of the newer versions of the book. Take me a moment to draw this up, folks, and then we'll comment on it once I get that part done. This representation of truss, you may notice something right off the bat, and that is that I'm not going any more serious lengths than just drawing lines here to represent that these are two force members. And we can do that with a truss because, quite frankly, even though it's a two force member, again, we don't care what the two force member shape looks like. It's just the fact that it's got two pins, two pinholes representing it. So, in fact, if you look at the truss that's drawn up in the book here, this is directly out of the book, they just use lines. So this is one of those few times we can kind of deviate away from actually trying to get too artistic here to show exactly what things look like. So there's that. This truss here can be defined, as you can see, by a grand total of 1, 2, 3, 4, 5. I got a grand total here of 5 members, and we usually name the members in accordance with the pins. So for example, if this is pin A and that's pin B right there, then that's member AB. If this is pin D, then there's member AD. Here's DB or BD, whichever way you want to go. DC, CD, same thing. BC, like so. So 5 interconnected, 2 force members. Notice there's no applied forces on any of the 2 force members, but I am showing an applied force here of 5,000 newtons pulling down on pin C. The problem statement for this one, folks, if we look at the narrative, there's not a whole lot in this narrative here. There's nothing ambiguous. It's determine the force in each member of the loaded truss. Determine the force in each member of the loaded truss. Now, a moment ago, I commented on the idea that the method of sections can sometimes get us more directly to what we want than the method of joints. Here, in this particular problem, we're being asked to solve the forces in each and every one of these member forces. That type of an ask usually lends itself well to the method of joints because it's designed to give us everything. Well, let's say, on the other hand, let's say that the problem had merely said, hey, I don't care about anything else. I just want to know what the force is in this member right here in AD, and you don't care about the rest of them. In a situation like that, the method of sections can get you more directly to that and maybe make it a little bit quicker, a little bit easier for you to figure that out. So that's the difference between the two. But again, as we'll see when we get there, they literally are the same thing, just kind of cloaked and differently because they look different. In this truss that we see right here, the dimensions tell us something important. If we look, we got a 5-meter leg here, a 5-meter leg here, a 6-meter leg here, and a 6-meter leg down there, meaning that this is a parallelogram. Important because if we know that this is a 45-degree angle here, and this again is a parallelogram, then we also can assert, even though it's not in the original diagram from the book, we can assert that this too is a 45-degree angle right here, again because of the nature of the parallelogram. So now, the task at hand, again, want to know all the forces and all the members. In other words, this 5,000 Newton force here, how much force does that impart in this one? How much does it impart in that one? And so on and so forth. Before we go any further, let's remember something ultra important. When I have a two-force member, regardless again of what its shape looks like, folks, let's remember that by the nature of a two-force member, the forces can only exist on a line drawn through the centers of the two pinholes. So if I got a line that goes through these centers, then I know that my forces can only exist on that line. So I might have a force here, might have a force here on that line. Let's also remember that those forces, depending upon which way the arrows are pointing, will create either compression in the two-force member. So in other words, if I had forces that were pointing in on the two-force member like this, they're trying to compress, squeeze together that member. On the other hand, if my arrows are pointing away from the member, then those are trying to pull the member apart. That's tension. All right? Because of that, and going along with the same idea, that means whatever forces are occurring in these members here, those forces can only be causing tension or compression on the member. And a part of analyzing trusses is not only to figure out how much force is in each member, but whether or not that force is causing compression or whether it's causing tension. So we need to be able to figure that part out. All right, we need to be able to figure that part out. And there's a very simple rule we're going to apply. I'm going to come back to that. I just want to preface what we're going to do here to let you know that's a thing. All right, that's a thing. We need to know if we're in compression or tension. So now we're going to figure this out. Again, the ask is what are the forces in all these members? We're going to use the method of joints. The method of joints, folks, follows a simple recipe. Let me write this, then I'll talk about it. And you definitely want to get this list into your notes. This first step seems like a lot, but it's pretty straightforward here, folks. In the method of joints, and I can't hammer this point home enough. There is no such thing in method of joints specifically in which you don't start with step one being a free-body diagram of the entire truss kept together, but only isolated from its support loads. All right? So in this case, if I want to do the free body diagram I'm talking about here, then if I look at pin A, I already know that pin A is a pin, therefore it's going to have an X force and a Y force. So let's do the usual here. Let's give ourselves a standard X and Y axis. And for the most part, the standard axis is going to work very nicely for us here. And in this case here, I'm going to kind of take the cheap way out when it comes to doing the free body diagram. I'm not going to redraw the whole thing. But I'm going to get rid of this pin here. And I'm going to, so I'm showing this now isolated from the support. It's no longer there. I'm going to reconnect this just so it kind of looks nice and clean. and I'm going to show my pin forces. So if this was pin A, and I know for a pin I'm going to have an X and a Y force, so maybe I've got my Y force and maybe it's going down. Do I know it's going downward, by the way, folks? Do I have any clue that that's going downward? No. Do I care? I'll let the math straighten that one out. So there's AY there. Let's assume I got an AX going off in this direction right here. Once again, I don't know the direction of it, but I can safely say that, again, my math's going to figure it out for me. And then lastly over here, I'm going to have the force on roller B. And again, we already know from what we learned back at the beginning of chapter 3 that forces on rollers are singular forces drawn normal to the plane of contact. So in this case here, I can get rid of all of this. Again, I want to make this look like a free body so that this stuff is all gone. Bring this together though. And now as far as the force here on B goes, again, roller force, single force. I don't know, since I threw this one downward, let me take a guess that this one here is going upward. And I'm just going to call this force, force B. So in my first step for the method of joints over here, I have completed at least the first segment of that, in which I've done now a free body diagram of the entire truss. I did not take the truss apart at all, folks. Free body diagram of the entire truss. I've isolated from its supports, and now I'm going to solve for those support loads. I got 3 unknowns, 3 equations of equilibrium in the budget here. So let's do the same old, same old. And by the way, you just heard me say it. Let's do the same old, right? Now we're at a point, and if you're not there, you need to get there. Now we're at a point where we say, I've already drawn a free body diagram. I now apply the equations of equilibrium. That's it. I mean, that's always the play here, folks. Once you got a free body diagram, we always go to, now, the equations of equilibrium. So I'm going to sum forces up in the x direction. What have I got here? If I sum up forces in the x direction, and I'm looking at the entirety of my truss, that 5,000 Newton force was drawn straight down, so that's not an x force. Straight up here, straight down here, not x forces. The only x force I got is ax over here. So I've got ax, which by the way is going in the negative direction, so negative ax, and I don't have any other x direction forces. So since I don't have any other x direction forces, this has got to be equal to 0, because the sum of the forces has to be equal to 0, and that simply tells me that ax is 0. There is no ax here. So from this equation right off the bat, we know that ax is equal to 0, which means there is no ax force. Now in a moment I'm going to get rid of that, but this also brings us back to something important we talked about too, and that is, once we know the value of a force, always show the value of that force on your free body. You don't want to leave it as an unknown because it's no longer an unknown. So this is 0 right here, and honestly, again folks, if it's 0, then why do we have it? Let's get rid of it. So I'm going to get rid now of this force because there is no force there. And let's continue with our equations of equilibrium. So if I sum up forces now in the y direction, what have I got? I've got B going in the positive y direction. I got AY going in the negative direction, so minus AY. And then I got this 5,000 over here also going in the negative y direction, so minus 5,000. So there are my 3 terms, my 3 y equations, and they're equal to 0. So what can I take away from that? Well, what I know is if I take that negative 5,000, I slide that over to the other side of the equal sign, it's going to become a positive 5,000. So that tells me that B minus AY is going to be equal to 5,000. All right? Don't know which one's which just yet, but we'll figure that out. So now, I have one more equation that I can apply, and that's the summing of the moments. Here, more than any place we've seen so far, here we're going to find there's wisdom in where we choose to take our moment equations. Because at the end of the day, we want to take the moment at some point, we don't have to, but we want to. We want to take the moment about some point in which we get rid of forces, and ideally we get rid of more than one whenever we can. In fact, there's a problem coming up later in chapter 4 in which we're going to solve an entire truss, all the unknowns, using nothing but moment equations. Remember, and I've talked about this before, just because, and the budget's always 3 by the way, 3 equations, but it's not a foregone conclusion that you have to use these equations. You can have three independent moment equations, and those two will lead us to answers. And we'll see that in action. But in this case right here, I don't know, think about this, folks. In this case right here, if I took my moments about point A, if I chose that as my moment center, then that force doesn't show up in the moment equation. B would show up in the moment equation. That one would show up in the moment equation, but again, that one wouldn't. But that would give me an equation with one unknown. I could then solve for B. Once I know what B is, I can slide into the equation that's on the board right there, and then I'm going to know what AY is. I could do the same thing by selecting to do my moment equation about B. Could do that. If I did that, then B is not in the picture, but AY is, and that one is, and I can solve for AY. I win either way. Either way is perfectly fine. The one place that I could make my math harder, if I'm just into making my math harder, would be, I don't know, let's say I'm going to do my moment equation about D, which you can. There's nothing wrong with it. But in doing that, then you'll have AY in that equation, you'll have B in that equation, and you'll have 5,000 in that equation. You'll still have another independent equation. The two of those equations combined, that one and this one right here, still solve the problem. So you don't go wrong, you just made the math harder. For us, let's go ahead and just take the moment about A. That's really, I think, the easy play here. So let's sum up moments about A. And again, in the nothing's new here department, notice how we write that out. We're saying, all right, we're going to sum moments. The sub A says about what point. The counterclockwise symbology there to remind us that, hey, if that force causes a counterclockwise rotation, it's positive. If it causes a clockwise rotation, it's negative. We just never want to forget that, folks. Let's start things off here with, again, a reminder that AY will not show up in this picture because it passes through the moment center, but B does not. I look at B and I see that it's going to cause a counterclockwise rotation about A, so it's going to be positive. So B times its moment arm, which is the distance from here over its line of action, which is given to us as 6. So force B times 6, and again, positive because of the counterclockwise rotation on that. And then we've got the 5,000 over there. Folks, y'all should be able to see from here that the 5,000 is causing a clockwise rotation about A, so that's going to make that negative. So minus 5,000. And then we got to have our moment arm here. So this one gets a little bit funkier. We got to figure some stuff out here. So the moment arm, folks, is not inherently obvious. It's going to be this distance here, 6 plus this portion that I have right here. So remember, we're always looking for triangles, right? We're always looking for triangles, even when we got to draw extra triangles. So right now, if I drew in a triangle right here, I've got this. I want to know this leg right here. And what I see, I'm going to draw it over here, is I see a triangle that looks kind of like this one right here, where I've got a 45-degree angle here. I've got a 5-meter leg right there, and I want to know this leg up here, which I'm just going to call A for, or I'll call it ADJ for adjacent. So if you look at it, I see, again, a 45-45 triangle here. So adjacent and hypotenuse, that's cosine. So you can write this as the cosine of 45 is, by definition, ADJ over the hypotenuse, which in our case is ADJ over 5. So therefore, that adjacent leg that we're interested in is going to be 5 times the cosine of 45. And I'm not even going to bother to solve that. It's 5 times 0.707, so 3 point something. But I will just come over here and say, all right, my total moment arm then, again, the distance from A over to the line of action of this one here, so this distance from here all the way over to here is going to be 6 plus what we just figured out. So 6 plus, from way the heck over there, 5 times the cosine of 45. And that's going to take care of that moment arm. And again, folks, here in the equation, we've taken care of this force in the moment equation. We've taken that care of that force in the moment equation. This one doesn't show up, so that equation right there has got to be equal to 0. So now, with that, now we can solve this equation. You know, this whole mess right here is going to become positive over the other side, equal sign. So I can solve this now for B is going to be equal then to 5,000 times 6 plus 5 cosine 45. That whole thing is going to be divided by that 6 right there. And folks, when you plug it in and crank that out, that ends up being about 7,946 newtons. 7,946 newtons. Now, ultra important is that not only do we know what the value of B is, that calculation came out to be a positive number, right? It's a positive number, which means that the assumed directionality of B is correct. Folks, early in the course, I made the point that when our math tells us that the directionality of a force is not what we assumed it to be, you have a choice to either go forward with your arrow in the direction that you originally drew and just carry through the negative number, or you have the choice to stop and say, you know what, I want to change my arrowhead and make it go in the right direction. That is still valid, but I will say this. If there's any place in the entire course that I would suggest fixing the arrowheads so that they're going in the right way, this is it. If we had found, for example, that B was not pointing up, that it was really pointing down, it's easy to change that right now and get that directionality correct. It's not our case this time, but we'll see that be the case from time to time. Again, you don't have to, but as you're about to see as we continue on with method of joints, we're going to start in a few minutes, we're going to start taking apart these pins and doing pin three-body diagrams, and getting those directions right just makes it easier not to make a mistake. So this is the one place I'd say, yeah, you might want to consider doing that. All right, but having said that, now that we know what B is, we can solve for AY. In fact, if I want to, I could rewrite AY. So AY would be equal then to B minus 5,000. And if I take 7,946 and I subtract 5,000 from that, I'm going to get 2,946. So AY is going to be equal then to 2,946 newtons. And once again, that came out positive, which means our assumed directionality over there is in fact correct. All right? It is in fact correct. So, with that, now what I want to do is come over here to my diagram again. I know my directions are correct, and remember, we've said if we know the value of something, always put that value in. So AY, we know right now, directionally right, and that's 2,946 newtons. B, directionally right, 7,946 newtons. And together, everything you just saw right there, folks, completes step number 1. Now, questions on that one before I get rid of it, folks? Okay. Step two. Step two, folks, is a kind of a loop step, if you will. In step two, we're going to draw free body diagrams of pins. The whole method of joints, after we do the free body diagram of the entire truss, just relies on us drawing free body diagrams now of pins, as many as we need to solve the problem. And note this little side sub-bullet down here, folks. When we draw the forces on the pins, we're going to assume that all forces in the members, in the truss members, are in tension. We're going to assume that the member is being pulled apart, and then we'll let the math correct us as applicable, meaning that if you assume it's in tension and the calculation comes out with a positive number, then it was in tension. On the other hand, if the calculation comes out with a negative number, then the assumption of tension was wrong and the member's actually in compression. And this is one of those things too, folks, that, by the way, even before you go into these, you can, especially as we gain experience with this, you can look at trusses and kind of get an idea in some cases of what do you expect. So for example, if I really did have a truss member like this and a truss member like this, and I'm really truly pulling down right here with 5,000 newtons, wouldn't it make sense that this 5,000 newtons pulling down here would be trying to squeeze that member together, the member BC right here? Wouldn't it seem that that would be trying to squeeze those together, or that member together? And the answer is yes. So therefore, I'm going to assume, even before I do the math, that I would expect this one here to be in compression. At the same time, if this was a pivot point here and I'm coming down like this, then the only thing that's preventing this from just rotating like that is this member right here, DC. So as I'm pulling down here, it wouldn't surprise me that DC is going to be pulled in tension as it's trying to counteract this force right here. We're going to find that that's the case too, but let's let the math lead us there. So folks, just following now our own rule over here, we're going to go ahead now and start drawing free body diagrams of pins as needed to solve the problem. And again, I wrote that vague purposely because we don't know which pins we're going to choose. We don't know how many we're going to need to choose, because it's just depending upon what the problem's asking us for. I mean, if the problem's just asking for one or two members, then maybe one pin gets the job done. In our case, this problem is asking us to figure out everything, all the forces in this entire truss. So it's just a matter of picking a pin, doing a free body diagram, and picking off a few members, and then pick another pin and keep going until you're done. Now, this also brings us back to there's not necessarily a right or a wrong pin to select, but there are smarter choices than others. Think about this. When we do a free body diagram of a pin, all the forces are going to be concurrent on the pin, meaning that they're all going to intersect at one common point, which means that we don't have a moment equation available to us when we do pin forces because of that concurrency, because of the singular point. That means that all of those forces would have a distance of 0 from that point of concurrency, so there is no moment. Meaning that with drawing free body diagrams of pins, we only get the sum of the forces in the x and we only get the sum of the forces in the y. That's it. Meaning that we have an ability then of solving no more than two unknowns, right? So think about this. If I said, well, I think I'll start with pin D, right? I'm going to start with pin D. And I draw the free body diagram of the pin. Even before we draw it up, let's just remember, when we draw a free body diagram, we show the thing, and we show forces of everything that used to be in contact with it. So it used to have AD in contact with it, it used to have DB in contact with it, and it used to have DC in contact with it. That would be 1, 2, 3 unknowns. So I would have one free body diagram, 3 unknowns, and a budget of 2 equations. So I couldn't solve that. On the other hand, if I chose pin A, look at pin A. If I do a free body diagram of pin A right now, I've got this known force hanging on it. I have one unknown here and one unknown there and a budget of 2 equations. If I choose pin A, I can solve for that force and that force. And then if you think about this, once I know what this force is here, then I can come back to pin D, and I would have a known force and only 2 more unknowns. Now all of a sudden I can solve it. See, I still would have to do the free body diagram, but I wouldn't be able to solve it initially. So following with rule 2, step 2 over there, we can draw free bodies of any pin we want, but the smart play is to pick a pin that's got only 2 unknowns and start knocking out some of the unknowns. So let's do pin A first. If I do pin A, there's the pin, the usual simple X, Y, coordinate axis like that. Now, just think about this. Again, there's nothing new this morning, department. When I draw a free body diagram, I draw a sketch of the thing, voila. I show its weight if I know it, but these pins have no weight, so nothing there. I show applied forces. If there's an applied force on this, then I show it there, and sure enough, this pin has got the applied 2946 over there, and we already know that that directionality is correct. So I'm just going to simply show that 2946 newtons, done. And then the last step, again, in the nothing's new here department, we show forces wherever we used to be in contact with something. But the thing that we're in contact with, the pin, was only in contact with two force members. And what direction do the forces in two force members go? So for example, in member AB right here, the force has to go along the line connecting those two pinholes, so it's going to be right along the line of action of AB. For AD here, the force is going to be along the line connecting those two pinholes, so right along that. So this is going to be real easy to show those forces, but there's one caveat. Over there, sub-bullet. Sub-bullet says, assume all forces are in tension. Meaning, folks, let's take a look at this. Let's say that I contemplate member AB right here. So if I draw member AB, it looks something like that. And I'm going to assume that the forces are in tension, meaning that if I drew those forces, then the arrowheads would have to be going away from the member, right? I'm going to call this, these forces, I'm going to call it AB in honor of the name of the member right here, right? So that shows the forces causing tension on the member. If we remember, old man Newton says, wherever we got corresponding forces, so here's the pin I'm drawing right now, right here, wherever I got corresponding forces, I got to draw the force as equal and opposite, right? So if I drew this arrow here going to the left here, that means I've got to draw the arrow on the pin going in the opposite direction, going to the right. So I'm going to show that as force AB. Now folks, for the same logic, when we draw the force on AD, that arrowhead's got to be going away from the pin as well. So I'm going to show that here as force AD. Now, there is a monumentally huge takeaway right here, folks. From the requirements of that sub-bullet over there, where we're going to assume that all forces are in tension, what that does for us is it tells us that when we show the forces on the pins, the arrowheads are always drawn away from the pin. Away from the pin. That assures you that you're assuming tension on those. So we're never going to have a force on an unknown member drawn towards the pin, where the arrowhead's pointing towards the pin. They're always pointing away from the pin. But now, having said all of that, here now is our complete free body diagram of pin A. Complete free body diagram. We have two equations of equilibrium, and by the way, let's make sure we're all clear. Here's pin A. We showed everything connected to it. Nothing happening over here has anything to do with pin A. So nice and simple, like you see. Let's sum forces in the x direction. I'm going to have here, so AB is tending, AB is a purely positive x force. So AB. Now AD is also tending towards positive x, so it's going to be plus. So it'll be plus, let's not forget this is a 45-degree angle right here. So plus AD, as I resolve this into its x component, it's going to be AD cosine 45. I've got this force right here, but that's a purely y-directional force, so I've got nothing going on with it. So right there's my x equation, that's going to be equal to 0. So one equation, two unknowns, can't solve anything. So let's just sum forces now in the y direction. Now in the y equation, this AB is not going to show up, right, because it's purely x-directional, but AD will. In fact, the y, resolved y component of AD is going to be AD times the sine of 45. So I got AD sine 45 tending towards positive y. This is a purely y-directional force, but it's going in the negative direction, negative y, so minus 2946. And that's going to be equal to 0. Now clearly, from this equation right here, we can solve for AD. So AD now, this will become positive on the other side of the equal sign. AD is going to be equal then to 2946 divided by the sine of 45. So 2946 divided by 0.707. So if we plug that in and crank that out, we're going to come up with 4,167 newtons. And folks, very important here, I mean super important, that came out to be a positive number. The fact that it came out to be a positive number confirms that when we assume that that was intention, it is intention. So now the way you want to do this, and this is very important, always put a T behind your answer here if it's in tension, and obviously we'll put a C behind it if it's in compression. That's, again, part of the specification of truss members. We can't just stop with a number. We got to state whether it's in compression or tension. This one here is in tension, and I'm probably going to add that over here as a sub bullet just as a reminder to us. So there, for each member, we're going to state whether we're in tension or compression. Now, from up here, if we take a look at this equation, we're going to rewrite it now. We see that AB, and we're going to move the AD cosine 45 over to the other side of the equal sign here, right? That's going to make it negative. So the AB is going to be equal then to minus AD cosine 45. And if we plug in our 4167 and multiply this time by 0.707, we're going back to our original 2946, but we're going to have a negative number here, so that's going to be equal now to negative 2946 newtons. And the fact that it is negative means our assumption that we were in tension is not correct. This is actually in compression. So we will put a C behind that. In fact, folks, and I want you to know I'm good with this either way. I got to see the C or I got to see the T. I don't care if you keep the negative sign there or not. It doesn't matter to me as long as you know that it's in compression or it's in tension. Now, because of that, we have two of our truss members known. Folks, a little trick here that I just want to encourage you to consider, because with a truss like this, there's a grand total of 5 members. It's not hard to lose count of which ones you got. But when we start getting a truss that might have dozens of members in them, you may lose sight of what's been solved and what hasn't been. So I just always, when I know the value of a truss member, I always put a little tick mark through it, just some kind of giving myself a visual reminder that I already know the value of that one. So it just makes it easier not to make a mistake. But now, folks, pausing here, breath of air. If you look at our 2 steps, we did the full free body, or the free body, the full truss together, just to solve the support loads. Did it, check, step 1 was done. Now in step 2, we're just doing pin free body diagrams. We're going to keep doing this until we get done with the entire truss. That's it. That's all there is to this entire process. All that remains for us is we just got to do a few more of these things and knock them out. So, all right, any question about this one here? If not, I'll get rid of it and we'll pick another pin. Matter of fact, as I'm erasing this, you should ask yourself, if you're doing this problem, where do you go next? Yes, fire away.
Did you label those forces that we found anywhere on the free body diagram?
These forces here?
The ones that were found, like that now have no values, would you put down like the main?
Yeah, I mean, I could. I generally don't, but there's nothing that would prevent you from doing it, nothing at all. So I think if I'm hearing what you're saying, you're suggesting that it wouldn't be a bad idea to, for example, on AD right here, I might just include in 4167 tension, and here I might include, 2946 compression. Is that what you were asking?
Yeah, on the pins, but yeah, something like that.
Yeah, I mean, you can label all you want to, since this is not technically anymore, we're not using this as a free body diagram, you can add it wherever you want to. A lot of times I'll actually And you'll see this on a problem coming up here in just a few minutes, where I'll actually kind of keep a running tally on the board of the paper, just so I've got a list. So any way that suits you, it's all good. It's all good. Any other questions, folks? Sweet. All right, let me clean this one up. And again, think about it. Where would you go next? What would you do? Knowing, by the way, there's no wrong answer. In fact, your question reminded me that I did want to keep track of those. Folks, I'm thinking pin C next. Now, you could easily go to B and solve that. You could easily go to D and solve that, but I'm just going to keep on this track here. Hey, if it's got two members, I'm gonna use that one. So how about pin C? So if I do pin C, I have the 5,000 Newton load that's hanging down from it like so. I have what I'm going to call BC going off like that, and I've got DC, or I'll call it CD in this case, CD going off like that, and I know that this is a 45-degree angle right there. So just like that, folks, and really want you to contemplate here how quickly I just drew that free body diagram up. You want to get to the point where you're not even thinking about it. It's like, yep, pin, got it. Applied load, got it. Member CD is attached to it, so I'm drawing an arrowhead away from the pin. Member BC is attached to it, I'm drawing an arrowhead away from the pin. That's it. It really, truly is that simple. And by the way, I will tell you right now, folks, that one of the problems that folks are going to have when you start adopting this process right here is and I'm not saying that happened to you, but I've had people in the past that will literally say, dude, it can't be that easy. Yeah, it is. It's exactly that easy. I mean, this is one of the things that engineers love to do, is make things more complicated than it really is. So it really, truly is that easy. Let's write equations of equilibrium here, folks. So if I sum forces in the x direction, I'm going to have minus CD minus BC cosine 45, and that's going to be equal to 0. If I sum up forces in the y direction, I'm going to have minus BC sine 45 minus 5,000, and that's going to be equal to 0. So there, just like that, are my two equations of equilibrium. Obviously, I can solve this one down here for BC. So BC is going to be equal then to minus 5,000 divided by the sine of 45, or minus 5,000 divided by 0.707, and that is going to get us to whatever I've got written down here, folks. Yeah, 70. So this becomes minus 7070 newtons, or in other words, 7,070 newtons in compression. So I'll put the C here to remind me that that is in compression. In fact, I'm going to go ahead and note that up here in my list. So I got BC now is 7070 in compression. And with that said, I can now solve for CD up here. So if I take this equation here, solve it for CD, I'm going to have CD is equal to minus BC cosine 45. But we've already determined that the value of BC, this is an important piece here, folks, the value of BC was minus 7070. So I'm actually going to have here now, I'm going to substitute that in with minus 7070. These two minuses are going to cancel each other and become positives, aren't they? So I'm going to have positive 7070 times 0.707, which is going to get us back to a positive 5,000 in this case. So this is going to be equal then to positive 5,000 newtons, and since it came out to be positive, then our assumption of tension is correct. Now, folks, I want to draw your attention here. I want to draw your attention to the fact that before we even did this problem, we looked at this and said, you know what, it seems like it makes sense that BC would be in compression, and sure enough, when you look over there, BC came out to be in compression. it made sense to us that CD was going to be in tension, and sure enough, as you see over there, CD is in fact in tension. So our math confirmed what we assumed was going to be the case. And with that, by the way, let's also note that we now have two more unknowns solved. Just like that. And so now when you look at it, there's only one left that we don't have an answer for, and that's this one right here. And folks, I can get this a couple of different ways. I could do a pin B. I could do pin D. If you think about it, with pin D, I know this one here. I know this one here. I would have a grand total of one unknown. Or I could, again, do the same thing with B. I know this one. I know this one. I would have just one unknown here. I am going to write in, though, what we did here before. So we said this one was going to be 7070 in compression. We said this would be 5,000 in tension. Fine. Let's do pin B. So as I start that diagram, the 7946 that's applied to it is shown. Now, very importantly, folks, here's where we got to be super careful. Remember, we're in a pattern where we assume that all member forces are in tension. But we already know that the member force in BC is not in tension. So what should we do? Should we show the arrow drawn away from the pin, because we tend to do that all the time, and then just put the negative number there? Or should we have this arrow come into the pin and put the positive value of 7070? The answer is yes and yes. This goes back to, again, you have to find the thing that resonates with you. Both ways work perfectly fine. Some of you may feel as though I just want to always draw my arrowheads away from the pin, and then I'll just put negative numbers when I need to. And that's perfectly fine. Some of you may be more like, no, I'm visual. I want the arrows pointing the right way when I know they're going the right way, and I'll put the positive value associated with that. Also fine. You have to, through practice of these problems, you have to find the thing that resonates with you. And I'll caution you here, folks. So you've heard me say this morning. You've seen me waving my hand saying, this is easy. Oh, trust me. When you actually start doing it, all right, applying it yourself, it's easy to get twisted up and turned around. So you got to practice these. Failure to practice these is a monumental mistake. All right, so don't do that. But in your practice, find the thing that resonates with you. I always like to just draw my arrowheads away from the pins and be done with it. So in this case here, this arrowhead going up like so. Even though I already know the value of BC, I'm going to write that in as minus 7070 because I drew this in tension, but the value in tension is actually negative. It's in compression. Again, that's just my way of preferring to do it. I'm going to have the unknown member DB going off like so. Let's call it BD. BD like that, and then I've got AB coming off like this, and AB was also shown to be in compression, so therefore that's negative. It's going to be negative 2946. Now that makes my free body diagram look a little bit different than what I'm used to, because I'm not used to seeing a bunch of negative numbers in there. But again, as long as we realize we're just following a convention, that's going to be perfectly fine. Or again, I could have easily flipped this around, drawn the arrowhead pointing to the right, and just made that a positive 2946. Either way is fine. You got to find what resonates and works for you. Now, folks, one thing we don't know right now, we've got some information on angles here. So, for example, we know this angle right here is 45 degrees. How? because if this is 45 and I draw a parallel line here, then that's going to be 45. What I don't have any knowledge of is what is this angle right here. This is another one of those where the authors can make it kind of look like it's like, well, it just looks like it's 45, right? Shouldn't it be? No, because we have differences in the dimensions here. So, no, it's not 45. The question then becomes, well, fine, then what is it? Well, again, we look for triangles here. I'm going to come over here and draw a triangle in like so. So here is my triangle. It's going to include my leg alpha here. We already know that that this leg here, I'm going to draw this out like this because it's getting a little crowded up here, that this leg here is going to be 5 times the sine of 45. That much we know for the length of this leg right here. Let's see. This leg right here is actually going to be 6 minus 5 times the cosine of 45. So 6 minus 5 cosine 45. But that gives me enough information to figure out what this angle is, because if you look at that right now, we can say that the tangent of alpha, opposite leg over the adjacent leg, so tangent of alpha would be the opposite leg, which is 5 times the sine of 45, divided by the adjacent leg, which is going to be 6 minus the cosine of 45. And folks, if you plug all that in and figure it all out, you're going to find out that alpha ends up being about 55.16 degrees. All right. So 55.16 degrees right there. And therefore, over here, also 55.16 degrees. And now, folks, with that in place, now we've got everything we need to solve this problem. So let's do the same old at this point. Let's sum forces in the, actually, before I even do that, I look at it and I think to myself, is there a way that I can do this with one equation? And the answer is yeah. In fact, all I need to do is sum forces in the x direction, and I should be able to solve for BD. I could even just do the same with summing forces in the y direction. I can solve for BD. So either way is a winner. Let's just sum forces in the x direction. If I sum forces in the x direction, I'm going to have so check this out, gotta look at this carefully. That's a minus x direction force, but the value is negative 2946. So I'm going to have minus 2946. Over here, I'm going to have plus, this is going the plus direction, so plus, but in this case it's going to be minus 7070 times the cosine of 45, and then minus BD times the cosine of 55.16. And that's all equal to 0. And of course, when we step back and look at that, we realize there's only one unknown in this one here, folks. So we've got everything we need to be able to solve for BD. And if I've done my math right, so let's take a look at this. Let's just write this out. So BD here should then be equal to 2946 minus 7070 cosine 45, which, by the way, 7070 cosine 45 is going to be 5,000. So minus 5,000 all divided by the cosine of 55.16. This is going to give me a negative number for BD, and if I've done my math right, I'm going to find that BD is equal then to minus 3590 newtons or 3590 newtons in compression. And that, folks, checks off the last one here, and with that, we have solved the problem. So, it's busy. You know, I think one of the first takeaways that we should all have when we look at problems like this, doing this first truss problem, a takeaway has to be that this one here had more moving parts than we're used to seeing. They're getting a little bit busier, they're getting a little more complicated. Obviously that was the plan all along, we knew that was going to be the case. But this is really where your discipline of kind of keeping track of things and being meticulous about following the negatives and the positives around, it's where it's going to make a huge difference. But it's all done in the context of it really is a very simple process here to do the method of joints. Does anybody have any questions on what you just saw right here? Cool, all right. Let's do one more. I don't think we'll go to, yeah, we'll do one more and we'll be done with it for today. Check out this truss right here, folks. At first glance, you might look at it and say, wait a minute, man, that's not a truss because those aren't forming triangles, are they? But yeah, they are. If you think about this, all these members are two-force members, right? So if you think about the line of action of forces in two-force members, the fact that this one here is curved, remember we've said many, many times, we don't care what the shape of the two-force member is. All we care about is it's got two pins and no weight, no applied forces. So that two-force member right there could easily just be straightened out and made into a triangular piece right there, couldn't it? So yeah, this is definitely a truss, all right. So the question for us on this one is, determine the forces in members AB, BC, and BD in the loaded truss. So AB, BC, and BD. In other words, I want to know what's going on here, I want to know what's going on here, and I want to know what's going on here. And we're going to use, of course, the method of joints to do that. So, if we just follow our own rules, step one is we're going to do a free body diagram of the whole truss, still completely intact, and we're just going to isolate it from its supports. And we see the usual here, folks, pin and a roller. In the absolutely nothing new department here, a pin and a roller for that one. So let's take a look here at what we might see on pin A. I'm going to, again, kind of take the easy way out here and just do my free body diagram using the original diagram, so we don't have to redraw the whole thing. So now with any old pin, we already know that there could be an X force, there could be a Y force. How about maybe there's an X force going off like this, AX, and maybe there's a Y force coming down like so. Let's call this one AY. We again don't know those directionalities, but we will soon. Over here, for the roller at C, we know there's going to be a single force here, and it's going to be normal to this plane. So I'll get rid of this. Bring this together like so. And in this case here, I'm going to go ahead and assume that this force is drawn upward. And we'll call this one C, since that's just what that roller was known as. So now, that is the first part of step one over there. Just again, do a free body diagram of the entire truss. All we did was we isolated it from its support loads. Now we're going to solve for the support. So if I sum forces now in the X direction, what have I got? I've got my force L. By the way, I didn't do it just yet, but need to. X, Y. I can't call L an X force unless I've identified that that's my X direction. So L is going in a positive X direction like that, so it's going to be L, and then I got AX over there, which is going in the negative direction, so L minus AX. When I look at AY and C, I see those are both purely Y directional forces, so they're not going to show up in this equation. So just like that, that's going to be equal to 0, and that tells me right now, folks, that AX is going to be equal to L. Two things. I know what its magnitude is. I don't know the value of L, but it doesn't matter. But since it came out positive, that also tells me my assumption of directionality was correct. So over here now, sticking with the plan that we always do, once we know the value of something, let's change that. Let's make this value L, like so. Let's continue on over here. If I sum up now forces in the Y direction, I'm going to have, let's see, I'm going to have C going in the positive Y, minus AY, since that's moving in the negative Y direction. And L's not in the picture, nor is, well, L and L are both not in the picture, so set that equal to 0. That merely tells us that C and AY are the same value, we just don't know what they are just yet. So now we need to sum a moment somewhere. So how about we sum moments about point A? Because remember, our choice of moments is helped when we pick a moment center where we get rid of as many forces as we can. So if I choose A right here, that's not in the moment equation, and that's not in the moment equation. So I'm going to sum moments about A. Counterclockwise, as positive as it always is. Now let's take a look. That C value over there. C, with respect to A, is going to be causing a counterclockwise rotation. So because it's counterclockwise, I'll have positive. And then the moment arm is going to be the distance from A all the way over here to the line of action of C. Now, the only dimension I've got was merely that this shape here was a semicircle, so of radius r. So if that right there represents one radius r, that's another radius r, that means this distance from here to here is twice the radius, or 2r. So C times 2r, like that. Then I've got L. Now L, a little bit easier to see if we slide it back on its line of action here. So slide over its line of action back here, it's pointing to the right. We should be able to see rather readily that that's causing it clockwise around A, so that makes it negative. So minus L, because it's negative, times its moment arm. Now folks, the moment arm, remember, is the distance from here up to the line of action of that force, which is this distance right here, but that distance is the same as, again, the radius r. So L times r. And that's the only that's the only terms that are going to be in my moment equation, so that's going to be equal to 0. So with that, I can readily solve now for C. It turns out that C is going to be equal then to L times R divided by 2R. The R's will cancel. I'm left with L over 2, so C is merely going to be L over 2. And since I know what it is, I'll come back over here. By the way, it came out positive, so our directionality assumption was correct. So now I've got L over 2 here. And we already asserted from up here that C is equal to, or AY is equal to C, so this is going to come out to L over 2 as well. And it came out positive, so therefore, its directionality was correct as well. So okay, there's step 1, done. Now, pick a pin. At this point, it really simply does boil down to, we're going to pick a pin. Before I erase this, just want to double check. Any questions about what is right there, anybody? All good? Okay, let me get rid of this. So now I'm going to pick a pin. Let's think about this. I could pick pin D. If I pick pin D, I'm going to have 1, 2, 3 unknowns. I don't go anywhere. I could pick pin B. 1, 2, 3 unknowns. I'm not going anywhere. C, that's a possibility. A is a possibility. 2 unknowns in both cases. So let's take A. So let's do pin A. There's the pin, the usual XY axis system. We already know that on this pin, we have got the force L over 2 going down like this. We've got the force L coming over like this. We know we're going to represent the force in member AD as an arrow pointing away from the pin, because we're assuming everything's in tension. But the question becomes, what direction does that arrow point? Now, I will say that it is not unusual. When you look at this at first, you might think, well, man, I need to come up with like some sort of a tangent line right here or something like that. It's a common mistake, but it's exactly what it is. It's a mistake. Here's where we have to remember one more time. We couldn't care less what the shape of a 2-force member is. All we care about is that the force in a 2-force member is drawn on a line that passes through the pinholes. So in this case here, the force that is in member AD is going up like this, because again, we're on this line passing through these 2 pinholes, and because that distance and that distance are the same, their radiuses, that means this angle right here has got to be 45 degrees. So look at that, folks, just like that. Very fast, very simple free body diagram. And I'm almost done. I haven't contemplated AB, so I got AD, now I got AB here. Again, arrow drawn away, assumes tension. So now my free body is done. 2 unknowns. Let's do the equations of equilibrium here. So if I sum up forces now in the x direction, I'm going to have, starting things off with AB going in the positive direction, or positive x, like that. AD is also tending towards positive x, so I'll have plus AD cosine 45. And then I'm going to have minus L here, so minus L, and that's going to be equal to 0. So I got 2 unknowns in that equation. I can't really do anything with it, no problem. So let's sum forces now in the y direction. And in this case, I'm going to have AD here tending towards positive y, but it's going to be AD times the sine of 45. Minus L over 2. And that's equal to 0. So that means that AD, if I solve for AD, I'm going to have AD is going to be equal then to L over 2 divided by the sine of 45. So this whole thing divided by 0.707. And folks, when you plug that in and crank that out, we're going to end up with AD being equal to it's going to be equal to 0.707 times L for AD. So it came out positive, tells us that it is in fact in tension. So AD is equal to 0.707 times L in tension. Got that. Now here we can solve for AB. So with this one here, we got AB is going to be equal then to L minus AD cosine 45. And folks, if we plug that all in and crank that all out, we're going to end up with AB, AB being, it's written here somewhere, yep, there it is. This is going to be 0.5 times L. And since that came out positive, then it's going to be in tension, like that. So AB now, 0. Whatever I said, 5 times L, also in tension. And just like that, we've knocked out a couple of these. Now, it is worth noting, folks, that we actually were never asked to solve for AD, but you'll notice here it was actually rather easy and kind of necessary in this case to solve for AB in order to be able to do that. All right, any questions there? Cool. All right, so let's now do the next pin. Let's go to pin B, because I definitely want to talk about pin B. It's an interesting one. So if I now do pin B, let's look at what we have. We have member AB, which we just said was 0.5 L in tension. So I'm going to draw, using the same coordinate axis as I did before, I'm going to draw this force away from the pin and show it as 0.5 L. I've got member BC, I'm drawing that one away from the pin, don't know it yet. And I got member BD here, going upwards like so, and there's my free body diagram. Just like that, very quickly. Now, let's do the same old, folks. I have the pen dropsies this morning. If we sum up forces in the x direction, we're going to have BC minus 0.5 times L, and that's going to be equal to 0, which means that BC is going to be equal to 0.5 times L. Came out positive, therefore it's in tension. Done. So now this one's knocked out. If I sum forces now in the y direction, I'm going to have BD from right here. I was covering it up, BD. And there are no other y direction forces. Therefore, according to my math, BD is equal to 0. That should leave you wondering, what? How could it possibly be that in a real life truss, if this thing is loaded up, that force right there could have, or I'm sorry, that member right there could have no force in it? In real life, it can't. In real life, the thing is going to have weight, so therefore there's got to be a force in it, right? Also in real life, it's not hooked up as merely a pinned connection, right? So it's going to actually be supporting some loads, but this illustrates, I won't call it a flaw, I'll call it a limitation of the analysis where we use two force members as our way of analyzing trusses. From time to time, we're going to see what we saw right here, where one of our members has 0 force in it. It's what's called a 0 force member, aptly named, right? Now, the question becomes, is there a way to spot them? The answer is yes. Anytime we have a pin, I want to focus on pin B here. Anytime we have a pin that has a grand total of only 3 members attached to it, and if 2 of those members form a straight line together, then the third member will always be a 0 force member. We can do the math to prove that. We're not going to, but that will be the case. Now, does that matter? Not really, because we can always let the math show us that. But you'll find with experience on this, the more you can spot those things and take them out of your system, the better. But folks, I want you to see this here. We did a grand total this morning of just 2 problems. We used the method of joints on both ones, and what we saw was a systematic, just follow the recipe way of solving these things. The task at hand for you all is to do that, run a few of these problems, in other words, work them, and follow that recipe and prove to yourself that, yeah, you're ready, you can do those kinds of things as well. It will take you where you want to go every time, but with a caution. Be meticulous. Watch those negative signs, folks. They will mess you up fast. Any questions on this one? Let's be done. And we'll see you guys all on Thursday. We'll pick this up from here. Thursday, we'll move a little bit more method. We'll do one more method of joints, and we move right into method of sections, and we'll go from there.